Hi everyone, my name is Tareq Eddir. I'm from Fluxtrol. My co-authors are Rob Goldstein, also from Fluxtrol, and Rob Haun from Anspanner. Our presentation is titled Investigating the Benefits of Soft Magnetic Composite Inserts on Energy Efficiency in Cold-Wall Billet Casters Using Computer Simulation. Okay, so for the outline, we'll begin with the cold-wall billet induction casters background. Then we will talk about the geometry description, followed by the simulation description, and then we will talk about the results for the electrical parameters, which is the important aspect of this presentation. Then we'll show some current density results, and then we will conclude and go for some questions. Okay, so for the background, demand for titanium and titanium alloy powder has increased substantially for additive manufacturing, aerospace industry, defense industry, and other industries over the past decade. Powder is manufactured through various techniques, such as IGA, which results in a relatively non-uniform powder size distribution. Additive manufacturing of titanium and titanium alloy parts requires a uniform powder size, which results in low yields of acceptable powder sizes. Those unacceptable powder sizes are recycled through cold-walled billet casters. The cold-walled billet casters, the cold-wall induction, has many benefits for purity and practical reasons, but they have a low electrical efficiency, which is what we're trying to address in this presentation. Adding soft magnetic composites have shown to increase efficiency of cold crucibles and help reduce power demand and improve billet quality for the systems as well. Okay, so on to the geometry description. A typical application begins with a titanium puck as a starting point, where the powder to be recycled is deposited from the top, while induction coil is energized and the melting process starts. As the powder is combined with the billet, it is being simultaneously pulled from the bottom. Once a desired length is achieved, that billet can be used for a depowder manufacturing process such as IGA. If you look at the picture to the right, this shows a cross section of the process. What we see here of the black arrows indicate a current direction. As the current, which is alternating current, is flowed through the coil, an opposite current is flowing through the fingers and another current is being induced into the billet. The fingers are water cooled to compensate for the power from the induced current and also from the radiation from the billet. These fingers are separated to allow for a current path that's shown here in each of the fingers, and also there's a slit which allows for some of the magnetic fields to pass through. This design, these geometries can be optimized for different applications, but that's not investigated in this study. Okay, so onto the simulation description. We used Flux 3D FEM software, which is a commercially available software provided by Eddir. We used 3D geometry. For this simulations, we use electromagnetic physics only. We understand that the process is actually a magnetohydrodynamic process, but for faster turnaround of simulations and easy comparison, we only use electromagnetics. We used 1000 amps RMS at 5 kilohertz for all the simulations for easy comparison. For the electrical resistivity of the load, we used 1.7 microohm meter, which is a typical value or close enough value for a typical hot titanium material. For the magnetic shunts, inserts, and rings, we use Fluxtrol 100 material properties. And to simplify the simulations and reduce the size, we use the 1/24th of the system, which is 1/2 of a finger, and then we have 12 fingers in the geometry. On the picture, you'll see where we added soft magnetic composites. We have the inserts here at the top and bottom. Those we could switch to copper or to inserts. And then we have the rings. We have a top ring and the bottom ring. And then the final thing is the vertical soft magnetic composites. That's what we call a shunt. And those can be used in different combinations, as we will see in the next slide. So onto the electrical results. This is the slide that shows the electrical efficiencies and the power distribution in the different components. What we see here is the different cases, the different concentrator uses, and then we have the voltage, the power in the load or the billet, we have the power in the coil, the power in the mold, and then the power in the soft magnetic composite, which combines the powers in the rings, inserts, or shunts wherever applicable. And then finally, the final column, we calculate the efficiency, which is calculated by dividing the power in the load divided by the total power. When we look at the bare case, we see that the efficiency is about 29.2% for this case. And then when we add the inserts, the efficiency is increased by about 11.5%, so about 40.8, about 41%. This is about 11% increase. This is a very substantial benefit. When we add rings and inserts, what we see is about a slight increase as compared to inserts only, to about 41.2. When we add rings and shunts only, in this case no inserts, we actually see a slight drop in the efficiency. So we go from about 29 to about 28. And then finally, when we add rings, shunts, and inserts, we get about 40%. And I think what this table shows us is that the use of inserts is the most substantial combination that we can use, the most substantial change addition. The rings and shunts, they may have other benefits other than efficiency, but when we look at electrical efficiency only, they may provide some benefit, but without inserts they're not quite as useful. So in this slides, we look at the current density distribution or current density contour map for the different cases. On the left, we see here a bare coil, and we could compare the different current densities. It may not be easy to see the difference. We have a slide showing a graph we'll show later. But by looking at these slides, what we can see is using inserts, looking at the cases with inserts versus the cases without inserts, what we can see when you use inserts, we have the power distribution, the current density distribution actually drops deeper into the billet as opposed to being concentrated a little bit more at the top, and we see that with as we see in the bare coil here and the rings and shunts only here. So again, this sort of matches the results we see with the efficiency, that the use of inserts is the most substantial in terms of efficiency increase, and we see a similar behavior for the different cases. The next slide here, we are looking at the current density distribution or current density contour maps for the mold. And again, we sort of see somewhat of a similar behavior where we see the cases without the inserts, the current density distribution on the fingers is somewhat distributed vertically or uniformly on the fingers, as the case with where we have the inserts that has less heating on the fingers, and this tells that the magnetic field is entering a little bit lower into the billet area and then exiting a little bit higher. So this gives us more of a vertical or more of a tangential magnetic field as opposed to the cases without the inserts. Okay, so in this slide we look at normalized current density graphs, and what we've done is we've taken a line at the OD of the billet, if you look here at the picture to the right, and we've plotted the current density and normalized for the different cases. What we see clearly is two different regimes or two distinct behaviors. The cases where we don't use inserts, like the bare coil and the ring and shunts only, the current density drops a little more drastically or quickly than it does in the cases where we have inserts along the height. So while we don't really see clear difference case to case, what we see is a difference between using inserts or no inserts. Okay, so to conclude, 3D simulations were made to predict electrical parameters and efficiencies in different cases. The results show that using soft magnetic composites for cold-walled billet casters increases electrical efficiency. What we've seen is adding rings and shunts only has no benefit or shows no substantial benefit on electrical efficiency. However, when we consider the chamber heating or the caster size, rings and shunts can be useful. But when we look at them from an electrical efficiency standpoint only, they're not beneficial or as useful as using them with inserts. The addition of inserts for cold-walled billet casters can increase the efficiency by about 10%. These simulations considered an existing mold design. We believe that further improvements may be achieved with an optimized design. And that concludes our presentation. Thank you for your listening, and if you have any questions, we'll be very happy to answer them.